So we have been looking at finite difference method that is used for discretizing boundary value problems as well as partial differential equations, and in particular in my last lecture I was looking at a partial differential equation, Laplace equation, and then we approximated the partial derivatives in spatial directions, and then what results is a set of linear algebraic equations. So we start with a partial differential equation, and then process of discretization resulted in set of linear algebraic equations. The problem was, so we had this partial differential equation. So x and y are normalized spatial coordinates, and then we have this partial differential equation that holds on the interior points, and then I said this was an example of a furnace, and then we use finite difference method to discretize this. What you get here is a set of linear algebraic equations. What I want to show again with the same example is that it depends upon the method you choose to discretize. Okay, it is not that this particular problem and finite difference method will always yield set of linear algebraic equations. I am going to do one more method called method of lines, which will yield ordinary differential equations, boundary value problem. So depending upon how you choose to discretize, you will get different types of approximations from the same problem. That is very important. Okay, and using the same method, same approach, that is finite difference. Okay, of course when we use some other method which we will be discussing, for example starting from towards the end of this lecture and next lecture, we will talk about orthogonal collocation. So that is another way of discretizing, that of course will yield a different way of formulating the approximate problem. So here we had these boundary conditions at x is equal to 0. We have condition that t0y is equal to t star. Then at x equal to 1 we have this condition t1y is equal to t star. The third boundary condition is again, so it is like saying that three walls are insulated and there is a convective heat transfer from one end. At y equal to 1, at y equal to 0 we have T temperature, at x 0 is equal to T star. So three walls are insulated, and the fourth one we have convective at y equal to 1 we have this boundary condition . So we have these four boundary conditions, and when we use finite difference method, what we got was a set of linear algebraic equations. What we had done was we discretized the domain. So this is 1, 2, 3 and so on. So we discretized the domain, we constructed, we demarcated grid points along y axis and along x axis, and then we imposed the partial differential equation at the grid points, or in the terms of finite difference method we force the residual to 0. Okay, we force the residual to 0 at the grid points, and this forcing residual to 0 at the grid points gave rise to large number of algebraic equations, and same thing is true about boundary conditions. We used finite difference at the boundary, and then we get additional equations at the boundary. So total number of equations that we have finally is, how many equations you have, how many variables? You have nx plus 1 cross ny plus 1 equations and you have same number of variables. Okay. Now instead of writing those equations again, I want to just point out something. If you actually try to rearrange this, what you get is set of linear algebraic equations, and if you rearrange them into a matrix form, the standard Ax equal to B form, then you get a very special kind of matrix. I don't want to write the matrix, I just want to show how it looks graphically. Okay. It's a special diagonal matrix, it's a sparse matrix what you get here, and so this matrix will have non-zero elements along first 3 diagonals. There will be a lot of zeros, there will be a non-zero diagonal again, there will be a 0 here, 0 diagonals and 0 diagonals. So you get a sparse matrix here if you rearrange all the equations. So this is I am T 1 1, or I think you have to eliminate the boundaries. So you get T 2 2 to T nx ny. If you eliminate the boundary conditions and then collect all the unknowns together and write this as one equation, you will get this. You will get a vector B here, which is coming out of f of x, y, the values of f of x at different points, f of x, y at different points, and then so this is, see this here in this case, this is the source term, and as I explained to you that the sources, if you are modeling this particular room, okay, then the sources would be each one of you, each one of you is a heat source like a 40 watt bulb, and the distribution of these bulbs can be given by f x y, at which points these bulbs are located, and then that would lead to a particular solution, a particular temperature distribution. So the solution here, actually the true solution, is a surface with one temperature value attached to each point, each xy in this. We are not able to solve this equation at every point, we are able to solve it only at finite number of points. You will get a good solution if you create more number of grid points. Okay, the solution will improve with more and more number of grid points, but their computations increase with more and more number of grid points. Okay, and this matrix which you see here, which you will get, will be a banded matrix, and this will be a sparse matrix. This is a side note that we'll be looking at sparse matrices a little later, but I just want to point out that I just want to provide a motivation for looking at sparse matrices. Why do we have to look at special methods for matrices which are filled with large number of zeros? Because you can save computation time when you have large matrices. Suppose this nx and ny, this happens to be, these are the number of variables, okay, and this matrix will be nx cross nx. See, these are the number of variables, so this matrix will be nx cross ny cross nx cross ny. This will be a huge matrix, just remember. Total number of variables are these. So this, if you eliminate boundary conditions, you will get something like nx cross ny variables in this vector, and this matrix is nx cross ny cross nx cross ny. So if you take 100 grid points, just imagine what is the size of this matrix. Inverting this kind of a matrix is possible, but you are wasting a lot of computer time because there are a lot of zeros, and those will probably give zeros when you invert. You don't have to waste your energy in finding a zeros on the right hand side. If you can devise some intelligent algorithm, you can save computation time. Okay. Now is this the only way of discretizing? We discretized both in x and y. Okay, we discretized both in x and y. First of all, why do I get this banded structure? Because when I discretize, okay, each equation will have only 5 variables associated with it. So I will have this variable, this variable, this variable, this variable. So this is I, this point is I comma j, this point will be I plus 1 comma j, this will be I minus 1 comma j, and so on. So 1, 2, 3, 4 points, neighboring points are appearing in each equation, and such you have large number of coupled equations. You have to solve them together simultaneously to arrive at the solution. Okay, the solution surface is being approximated by solving the equation at discrete number of points. Since it's an approximation, what you get is an approximate solution, cannot be the true solution. Okay, for this particular problem, in many cases you'll be able to solve the problem analytically. That's a different story. Okay, but if there is a non-linearity, then you are in trouble. For example, I can make this problem non-linear just by saying that this thermal diffusivity alpha is a function of temperature. Right now I assume constant temperature, probably if you are doing a modeling in this room, the temperature variation is not too much. It's a good assumption that alpha is constant, but if there is too much variation of temperature in a region where you are modeling, then it is worth modeling alpha as a function of temperature, and then immediately the equations which are linear algebraic equations will become non-linear algebraic equations. Okay, leave that aside, but let's not talk about non-linearity. Let's look at this problem again through another method called method of lines. Okay, so what I am going to do now, this is a method which belongs to the same finite difference class, or it could reappear when you do orthogonal collocations. Instead of discretizing in both dimensions x and y, I could choose to discretize only in one dimension, say x. Okay, and I want to retain the differential operator in y direction. Okay, I will discretize only in x direction, I want to retain differential operator in y direction. This is another way of discretizing. So this will give me method of lines. So what I am going to do here, is instead of drawing grid points in both x and y direction, I am not going to mark the, I am going to draw parallel lines, I am going to mark grid points along y, okay, and I am going to draw parallel lines here. Well, the lines in my drawing are not looking parallel, but I intend to draw parallel lines. Okay, so I am going to draw parallel lines here. Okay, I want to discretize only in one direction and not in the other direction. So, no, 1 minute, I have made a mistake here. Well, I want to draw lines parallel to x axis. So I want to draw lines parallel to x axis. Well, it's not really important whether you discretize, you discretize in x direction or whether you discretize in y direction, it's not that important. In this particular problem, because of asymmetric boundary conditions, it's good to discretize along x direction. So what I'm going to do now, I'm going to mark this variable. Now this is my notation. Okay, my notation is TIY. Okay, TIY is a variation of temperature along y direction along the ith line parallel to y axis. I have drawn lines parallel to y axis, okay, and TIY is the variation of temperature, okay, along ith line parallel to the y axis. Okay, I am just fixing xi. So this is my x equal to xi. This is the ith point, and TIY is nothing but, okay. So now the way I am going to discretize this equation now is, okay, now look at this equation, the way I have discretized this. I have discretized only in x, spatial coordinate x, I have chosen not to discretize in y. Okay. Now I have converted the partial differential operator along y to total differential because now x has been taken care because of discretization. Okay. So this becomes an ordinary differential equation. This becomes an ordinary differential equation. Now we have to use boundary conditions. We have to use boundary conditions, right? And boundary conditions, because of boundary conditions, you will get, is this one ordinary differential equation? How many you get? At all the internal grid points, remember, at all the internal grid points. So 2, 3, up to nx, and this will be, the last point is nx plus 1. So till nx, till last parallel line, we get these differential equations. So I goes from 2, 3 up to nx. So you get ordinary differential equations. You get ordinary differential equations, not one ordinary differential equation. You get coupled set of ordinary differential equations, right? Ith value or tiy is related to ti plus 1y and ti minus 1y, right? So the temperature on ith line is a function of temperature on this line and this line. Okay, is a function of, so what you get here is a set of coupled ordinary differential equations, not one ordinary differential equation. Okay, you get large number of coupled ordinary differential equations. Suppose we discretize with 100 grid points, internal grid points. 100 coupled ordinary differential equations need to be solved simultaneously. Okay, because neighboring variables appear in each one of them. And now we can use the boundary condition to complete the problem. So we have this two boundary conditions, T1y is equal to T star and T nx plus 1 y is equal to T star. You can use these two conditions to eliminate some variables. Okay, you can use this boundary condition to, or you may have to solve it as a differential algebraic system. Okay, so you have these conditions in addition, plus you will have to have two conditions which will now become boundary conditions for this ordinary set of ordinary differential equations. So those will arise because of this and this. So if I just write them in, well, we don't have space here. Okay, I'll write it here. This is one of the boundary conditions. Okay, and the second one will come because of discretization of this. Okay, and that would be KTI1 So discretization of this boundary condition will give you this set of equations. Okay, now what you get here is a set of coupled second order ordinary differential equations, which are these, subject to boundary conditions at y equal to 0 and at y equal to 1. Okay, so same problem, finite difference method, but instead of choosing to discretize in both the directions, if I discretize only in one direction, I get ODE boundary value problem. Okay, same original PDE, I get ODE boundary value problem. So it depends upon how you choose to discretize. Okay, this problem could yield set of linear algebraic equations if you choose to discretize in one particular way. This problem will yield set of ordinary differential equations boundary value problem if you choose to discretize in another way. So it depends upon how you choose to discretize the problem. Okay, now I am just going to write one more variation of the same problem. We have been looking at the steady state equation. What if I decide to look at in addition time variation. This is the steady state Laplace equation. What about time variation? If I include dou t by, then I'll have to, then discretization can yield, well then there is a problem in using method of lines, because if you discretize only in one dimension you will get another partial differential equation, so which you again have to discretize. So it depends upon the problem at hand. So suppose I have here a modified version of this problem. So the modified version I would just create here itself. If I add here, okay, and my right hand side is, instead of f of x y, I'll make it time dependent. Okay, and all these conditions at boundaries will hold for all time. Okay, all these conditions at the boundaries will hold at all time, and then I will also have initial conditions. So I'll have to give a initial distribution of temperature in the room. So what I want to know is how the temperature surface is changing as a function of time. Okay, when I am including time derivative here, okay, I am looking at the spatial distribution of temperature in this room or in a furnace or whatever the condition is, and then I am interested in time evolution of this temperatures, okay, not just the steady state. Okay, so this problem will also have additional initial conditions coming up. So the boundary conditions have to hold for all t. So this has to hold for all time t, including this boundary condition, and then you will have at t is equal to 0, you will have temperature at xy 0 is equal to some function, say h xy. So this is the initial condition. So this is the initial distribution of temperature in the room. Okay, and then I want to solve this problem. What should I do here? Can you suggest something? What if I decide to discretize in two spatial dimensions? I discretize in x and y. I leave temperature as it is. What will I get? I will get ordinary differential equation initial value problem. I will get ordinary differential equations initial value problem. Large number of ordinary differential equations which are coupled. Okay, so here if I now take, I am not going to completely write the solution, you can work it out. I am just going to hint at the solution. So I am going to call now T I J X I, or I am going to call T I J T is equal to temperature at xi, yj and t. So like in the previous case I have created a grid, here and so on. I have created a grid and I am at ijth point, the time variation I am going to write like this, and then well I will discretize this problem as dt I comma j t by dt plus alpha times, now I will approximate this as t I plus 1 comma j minus 2 t I j plus t I minus 1 comma j divided by delta x square plus so if I discretize in two dimensions I get large number of equations, okay, large number of ordinary differential equations in time, but in this case I will not get a boundary value problem. Just think about it. In this case I will get a ordinary differential equations initial value problem. Okay, so Right now we are not talking about how to solve these problems, we are just talking about transformations. We want to take a problem, transform it into a solvable or computable form. How to actually compute that solution, we'll come to that later. Okay, I want to separate these two things. I just want to give you a viewpoint that, well, if I take a partial differential equation or ordinary differential equation, I know from Weierstrass theorem that any continuous function can be approximated using polynomials. So I use Taylor series approximation, construct local approximations of the differential operator, and force the so-called residuals to 0. That gives rise to an approximate problem. Okay, approximate problem would look completely different from the original problem. A PD is giving rise to set of algebraic equations, linear algebraic equations. PD giving rise to set of ordinary differential equations, boundary value problem, or a PD giving rise to set of ordinary differential equations, initial value problem. So we bring all these into some standard forms and then we apply the standard tools to solve these problems. Okay, that is what you should realize. There is no unique way of coming up with a discretization. You could have your preferences solve the problem at hand. So in this place you can complete the initial conditions, you can replace all, you can remove the so this could become a DAE, differential algebraic system, with initial value problem, initial condition specified, or if you eliminate, it could be just ordinary differential equations, initial value problem. Okay, so till now we were looking at Taylor series approximation. Okay, and as I said, this is only one of the methods that are used for discretization. Other two methods are interpolation, polynomial interpolation, and then least square approximation. So now we'll stop here with Taylor series approximation. We'll now move on to polynomial interpolation, and let's see how interpolation can be used to discretize the same set of problems. What I have deliberately done is in the lecture notes is that I have taken same set of problems and discretized them using different approaches. Okay, so that you will get a better insight into what is really happening at the discretization stage. Okay, so now let's move on to interpolation. Interpolation is something which probably you are introduced in your undergraduate curriculum. Can anyone tell me what is interpolation? What is an interpolating polynomial? What is an interpolating polynomial? When do you do interpolation? Or interpolating functions? You are given a set of points and values. So you are given some set of, so you actually want to develop an approximation for a function, continuous function. Let's take a continuous function, say u, or to be very precise, let me see, to begin with polynomial interpolation. Well, you can also do functional interpolation, in general functional interpolation, but we are interested right now in polynomial interpolation because we will use the polynomial interpolation ideas to come up with approximations or discretization of some operators. Okay, so now polynomial interpolation is we are given some values of, say, dependent variable uz and independent variable z. So we know some values of u. Okay, just before I move on to this, let me clarify one point. In finite difference method, I kept on using equispaced grid points. Okay, it is not necessary that you should have equispaced grid points. That was only for the convenience of development, understanding. Actually, you can use non-equispaced grid points. Okay, now for example, if you are now when to use non-equispaced grid points and then how to space them will depend upon your understanding of the physical problem. Okay, see, for example, if you have a PFR, okay, if you have a plug flow reactor and let's say most of the action is in the initial part of the PFR and later the concentration becomes steady or it doesn't change too much, it becomes flat. Okay, it's worth putting more grid points in the initial part which are closer to each other and then putting sparse grid points later because there is not much thing happening at the end of the reactor. Okay, so this depends upon your understanding of the problem. In some cases you may want to place close grid points in the at the two ends and sparse grid points in the middle. It depends upon the problem. Okay, so there is nothing sacrosanct about equispaced grid points. Equispaced grid points only make development on the board simple, but in general, when you, and as a beginner you might start with equispaced grid point, but then if you know about some problem where there is more variation of a particular spatial variation in particular region, you can put closer grid points and then you can have sparse grid points at, so that depends upon your understanding of the system. Okay, so let's move on to this polynomial interpolation. Now what I want to do here is I have this function, uz, okay, as a function of independent variable z, and I know the function values at these discrete points, okay, at these discrete points in the domain. So I know, so this is my point number 1, this is point number 2, this is in general ith point, and this is my n plus 1th point, okay. From z1 to zn, I know value of a function, okay. Now what I want to do is I want to construct a polynomial which passes through each one of them, okay. I know this is a continuous function of independent variable z, okay. By Weierstrass theorem I can approximate it as a polynomial function, okay. Weierstrass theorem allows me to approximate it as a polynomial function. I want to construct a polynomial function that passes through all the points, okay. This is different from least square approximations which you do in your experimental work, where you fit a line. So the line may not pass through every point, that is least square approximation. We'll look at least square approximations little later, but right now we are concerned about constructing a polynomial that goes through every point, okay, that goes through every point. So my problem is to construct a polynomial Pz. I am going to construct a polynomial approximation Pz. Now this is alpha 0, alpha 1. If I have n plus 1 points, I can fit a polynomial of order n that exactly passes through all these points. I need a polynomial of order n because the polynomial must pass through every point. So this is the constraint, okay. So what does this constraint mean? So I have these points z1, z2, zn plus 1, I have these points, okay. What I want is that value of this polynomial at each of these points should be exactly equal to ui, that is an interpolating polynomial, okay. So I have this set of constraints, so alpha 0 plus alpha 1 z1 up to alpha n z1 raised to n is equal to u1, alpha 0 plus alpha 1 z2 and so on. So I get n plus 1 equations, I get these n plus 1 equations in n plus 1 unknowns. What are the unknowns here? Alpha 0, alpha 1, alpha 2 up to alpha n, there are n plus 1 unknowns, okay, and there are n plus 1 equations. How do you solve this? So this can be simply transformed into 1 z1, z1 square, z1 raised to n, 1 z2, z2 square, z2 raised to n. So this is simply solving Ax equal to b, okay. Well, unfortunately life is not so simple because it turns out that if you want to develop a higher order interpolation polynomial, nth order interpolation polynomial in general, above 3 or 4, this matrix here It looks very simple, right? Ax equal to b. This is known to you. These values are known to you. Function values are known to you right now. Okay. What you don't know is alpha 0 to alpha n, and you know this matrix, right? You know the point at which, so you know z1, you know z2, so you can create this matrix. We will see in the course of looking at ill-conditioned matrices. We will see that this is one of the highly ill-conditioned matrix. Okay, highly ill-conditioned matrix, difficult to invert. You can get so high order interpolation polynomials, if you just go by this brute force approach, can lead you to problems. Well, one way to get out of the situation is to use orthogonal polynomials. These polynomials are not orthogonal. These polynomials are not orthogonal. So that's why you get into trouble. If you use orthogonal polynomials, you can come out of this problem. And then this matrix is very nicely behaved and so on. But right now let's not worry about that part. Right now let's assume that this matrix is invertible. So how do I get alpha 0 to alpha n? So if this is my A matrix, and let's say this is my capital U vector, then, and if I call this simply as theta parameter vector, then you know, at least on paper I can write theta is equal to A inverse U, right? The A matrix is known to me, U vector, I know the function values at these points, theta I can get, what I get is an interpolating polynomial. Okay, this is called interpolating polynomial. Well, I am going to use the idea of interpolating polynomial to discretize boundary value problems, to discretize partial differential equations. What I will be getting there, or the method that is used to do that is called as method of orthogonal collocations. Why this word orthogonal comes into picture? We'll look at those details. But the basis is this, that if you know a value at certain number of points, then theta can be expressed as A inverse U. Okay, and this polynomial which you get here, if you are able to calculate all these alpha 0 to alpha n correctly, this polynomial will pass exactly through all these points. That is very important. Okay, this polynomial will pass through each one of these points. It's a nth order polynomial that passes through each one of these points. Now the trouble I told you is that constructing a very high order polynomial through large number of points is can give you to some ill conditioning. And when you are discretizing, see, we saw in finite difference method, what was the message, take home message, that you know, if you have more number of grid points, better the solution. Okay, so when you are discretizing, this is true for even for if you use interpolation approach to discretize. So you would need large number of grid points. Okay, but that would mean you have to fit a large order polynomial, and then you can get into ill conditioning problem. Now when I'm going to do the development of orthogonal collocation method, I am not going to bother too much about this ill conditioning. I am just going to develop a method and convey the approach. But what you really need is spline interpolation. Do you know what is spline interpolation? Cubic spline interpolation? Well, I have discussed it in detail in the lecture notes. I'll just give you a brief idea what is cubic spline interpolation. The exact equations you can see here in section 4.2, but let me explain the idea. The basic idea is this, that instead of fitting one giant polynomial of high order which passes through all the equation, we could choose to construct piecewise polynomial approximation. Okay, so I could construct one approximation between these 2 points, I could construct another approximation between these 2 points, third approximation between these 2 points. What I have to make sure is that these neighboring approximations are continuous. Okay, neighboring approximations are continuous. Typically what is done is that we fit a cubic polynomial between two neighboring points, okay, and make sure that they are smoothly joined, okay. So how do you make sure that they are smoothly joined? Well, we make sure that the first derivative and the second derivatives match for the neighboring polynomials, okay. So this is called as piecewise polynomial approximation, and this is many times required because so what is the idea here is that you still have the same number of points, okay. You still have ui, that is u zi for zi or I going from 1 to up to n plus 1, okay. You still have these grid points, okay. Now what I am going to do here in piecewise polynomial approximation, well, let me be little careful about the terminology. Piecewise polynomial interpolation approximation will be using in some other context, okay. So piecewise polynomial interpolation. So what I do here is that I fit a polynomial between two neighboring points, and then I make sure that there is a continuity between two neighboring polynomials, okay. So I will have a polynomial P1z which is alpha 0 1 plus alpha 1 comma 1. Now there are many polynomials, so I have to have, you know, a notation which is which has two coefficients. The coefficients will have alpha 0 1, so this is the first polynomial, 0th coefficient, okay. Then z minus z1 plus alpha 2 1 z minus z1 square plus alpha 3 1 z minus z1 cube, and this holds between z1 z z2. P2z is alpha 0 2 plus alpha 1 2 z minus z2 plus alpha 2 2 z minus z2 square plus alpha 3 2 z minus z2 cube. So this polynomial holds between z2, z and z3, and likewise, you know, between each segment I fit a polynomial in this approach. This is called piecewise polynomial approximation, okay. This is called piecewise polynomial approximation. Now how do I make sure there is continuity? I have to put some conditions here. So one condition is, of course, you know, these values. One condition come from these values, okay. The other conditions come from the derivatives or the smoothness of the derivatives. So other conditions arise. So this is the terminal point. So these are all initial points of each polynomial. Then we have these conditions which are continuity conditions. Pi z I plus 1 is equal to P I plus 1 z I plus 1. So essentially we are saying that the initial value of this polynomial is same as the final value of the previous polynomial, okay. Then you have condition dpi z I plus 1 by dz is equal to dp I plus 1, and the third condition is so to ensure smoothness we make sure that the value of these two neighboring polynomials at the common point is same. The first derivative of the two neighboring polynomials at the common point is same, and the second derivative of the two neighboring polynomials at the common point is identical. So these are the additional constraints which we impose. Okay, these are additional constraints which we impose. If you actually put all these constraints, then you need two boundary constraints. So there are different ways of specifying the boundary constraints. One of them is called as, you just look at the notes here. So free boundary conditions are, we need two more conditions at the two boundary points, at this point and this point. So those are free boundary conditions would be d2p. If you include these two boundary conditions, that at the two boundaries the second derivative is 0. Okay, if you include these two boundary conditions, then you get number of equations equal to number of unknowns. What are the unknowns here? Alpha values. Okay, how many alpha values? 4 into n. Okay, you can do some algebraic manipulations and finally reduce this problem to Ax equal to b, where A is a sparse matrix. The manipulations are given here, you can just have a look at it. But interpolation, when it is not possible to do high order interpolation, this cubic polynomial interpolation will be used. Okay, and that will lead to orthogonal collocations on finite element. So we'll get a method, finite element method, if you do, you know, polynomial interpolations on a smaller domain. So there are different ways of doing interpolation, and it's a very rich area. I am just touching the tip of the iceberg by talking about these two basic ideas, which I need to develop my further approach. So the next lecture I'll start using interpolation idea, not the cubic polynomial, not the piecewise polynomial interpolation, simple interpolation. Okay, nth order polynomial passing through all n plus 1 points. This simple idea I am going to use to develop method of orthogonal collocations. Okay, so by the method of orthogonal collocations we will discretize again boundary value problems and partial differential equations. Okay, so you will again revisit the same problems but through a different approach. Okay, so orthogonal collocations is a very popular method. In fact, it's a method which requires less number of grid points to get the same accuracy as that of the finite difference method. Finite difference method would require large number of grid points. This method gives better solutions with less number of grid points. So this is computationally less expensive as compared to finite difference method. Okay, that's why we want to go for polynomial interpolation.